Okay, good evening everyone. So today my team will be presenting to you about BioMEMS sensing. So for our group, we have 5 people. I'll be presenting first, followed by Yukun, Xingyi, Koshiki, and Chuhao. Okay. So for my topic, I'll be presenting to you about BioMEMS integrated microfluidic platform for BioMEMS application. So firstly, I will talk to you about my content, my introduction. I will talk about microfluidics, what is microfluidic fabrication, some microscope images, the demonstration of the device, some results, and lastly, the conclusion for my part. So, introduction to the paper is that we have a fully BioMEMS integrated microfluidic platform, and it has been demonstrated. And this novel integration process flow provides very flexible size microchannels in the BioMEMS chip. The platform has been demonstrated with BioMEMS integrated with the 120 GHz dielectric sensor. And the good thing about this is that it has a high reproducibility, it has a small size, and it's relatively cheap. And this makes it very good for BioMEMS or terahertz sensing application. Okay, so just to give you a brief overview, so we have the sensor here in the back end of line. This is the BioMEMS wafer on top. And we have another wafer below where you have the channel for the microfluidic. So this is the inlet outlet. Okay, so this is the concept. And before I continue, I would like to talk about microfluidics. So what is microfluidic? So it is the science of manipulating and controlling a small volume of liquids, usually in this range. So this is quite small, hence the name microfluidics. In network of channels in this range, very small. The good thing about using microfluidics is that it decreases your sample and reagent consumptions, lesser time for your experiments, and also cheaper for your application as well. So this is the fabrication of the sensor. So it is divided into 2 parts. The left side will be the BioMEMS sensor fabrication. The right side will be the bottom wafer fabrication. So it's very easy to do. You just do the etching, the deep etching for this case. This one's the second deeper trench etching. So when you have these 2 wafers together, you actually just glue them together. So you have this cross section. So these are some microscope images. So on the left side, A and B, you see the bottom wafer, the top view and the bottom view. And on the right side is the BioMEMS wafer, the top view and the bottom view. And this is the sandwich, the cross section of the sandwich itself. So where would the microfluidic go? So you can see these are the inlet and the outlet respectively. So inlet, this will be under the sensor, which will be sensed by the BioMEMS sensor. And this is the outlet, or the other way around also can. Okay. So the demonstration is as such. We are using the 120 GHz dielectric sensor, which includes the VCO transducer to detect the change in the dielectric constants and the detector itself. So this is the schematic of the dimensions. The dimensions are optimized to get a good flow from the microfluidics itself. So this has been optimized for this case. And so how do we detect it? Is by having the output of the VCO. It is filtered by the transducer and applied to the detector. And the change of the dielectric constant of the fluid itself will shift the passband frequency of the transducer. And we can detect it with a high sensitivity. So these are some photographs of the test chip. So there are an array of them, and this is a zoom-in version of one of the test chips. As you can see, the VCO, the transducer in the middle, and lastly the detector. So the microfluidic will be going from the left, will be underneath, and it will be detected in this part here. Okay, so how do we do it? Is by having, this is what we call a way for you to put the fluid inside. So it's exactly the same size as the chip. So you put the fluid in one inlet, then it will go up to the other outlet. And the flow rate is being controlled by Nemesis string pumps during the measurements. And these are some of the photographs. So for air, so this is a transducer, so it's measuring the one for air. And for water or other liquids, we can use biomarkers to actually see it. Okay, so some results we can observe is that if you're using different fluids, you are actually having different voltage measurements that is detected by the output This is the measurement from the experiment, and this actually correlates with the simulation whereby we are using 115 gigahertz as our tuning frequency, where the VCO is at 0 volt, and we can see that it is being attenuated at different values for air, water, and ethanol. Okay, so to conclude, a fully BioMEMS integrated microfluidic platform for BioMEMS has been demonstrated, and you can see the small channels that I mentioned earlier. And the good thing about this is we have a high reproducibility, small size, and also low cost, which makes it very good for applications such as, for example, you can use to detect different fluids. So my next presenter will be talking about one such application whereby he'll be using blood as one of our fluids. So presenting Yukun to talk about this.
Thanks, Ali. Ali just introduced the microfluidics MEMS to us. Why is it so attractive to us to do microfluidics? First of all, it's deterministic flow, because when we are trying to play with those droplets or fluids, we can determine how it flows and which layer it will go. And also the scale is very in the micrometer, which is around the cell scale. And we can control and automate the whole process by using valves and pumps. Also, the small reagents causes very minimum waste. So we don't need a lot of sample, and we don't waste too much for dust testing. Also, the high throughput, like let's say we can use because the fluidics we can make millions or hundreds of thousands to finish the testing or screening at one time. So that's all the motivation for us to use microfluidics MEMS. So for me, in my part, I will emphasize on one particular subfield about digital microfluidics. What do I mean by digital?
I guess, which is just one drop.
Here, as you can see, we have like two droplets here. Let's see. Two droplets, one green one, one red one. And this is, underneath is electrodes, and there is an insulator in the middle. We can, without magnet, without nothing, we can, by applying different voltages, we can merge them together into one large droplet. Or later you can see, we can split this large droplet into two or multiple parts. What do I mean by talking about digital fluidics? Now it's split. We can combine or merge or split into two and merge together. So that's it. So basically, by applying digital microfluidics, we can split from the other parts or merge them together, moving, or that's what we can see. How do we achieve this? At the bottom of the plate, there will be electrodes, and in the middle, there will be an insulator, like the droplet, keep the droplet again away from the insulator. And here we apply a phenomenon called electrowetting. So what's the electrowetting means? According to this very complex calculation, we can know that when we apply different voltages to the electrode, the contact angle of the liquid and the substrate will be controlled. By controlling this angle, we can achieve the moving of droplets. When it's very, very flat, it tends to maintain at the same position. And when we move this one side of the droplet at a high, very large angle, the other side very small amount of angle, then the whole droplet will move this way. So this is how we achieve the control of droplets. There are many applications for these techniques. For example, we can control at like say 20 or 30 droplets at the same time because we have multiple electrodes underneath. And we can like say control a droplet larger than a coin. And this one is very interesting. when we put a liquid and a solid together, when we apply the voltage, we can remove the liquid from the solid, meaning the solid will be remain there and the liquid will be removed from it. So we can separate them. That's how we apply this one to a blood testing. First of all, you can drop a piece of blood here onto the testing chip. Then you can see this one is the droplet we already have in the chip, which contains extraction solvent. Then we can manually move this droplet to the blood cell. After some time, all the biomarkers are traced, are reacted. We can further extract the droplet away. And for further processing, we can derivatize the extraction. So for this one contains the biomarker we need, and we can move it further for further processing. Not only for the fresh blood sample can be tested, we can also use this method for testing the blood on a punched filter paper. For the punched filter paper, it contains the blood cell. Then we can use the same method to remove the cell from the filter paper, just as shown here. So before I end my presentation, I will emphasize one point. For this one, it's mainly used for screening newborn babies. In a middle-sized hospital in the U.S., every year they can give birth to 140K babies. So all these babies, they don't have too much blood for us to waste and to test. So using this method, we can use very minimum amount of sample for testing. So it's kind of influential in the future medical testing fields. That's all my part. Thank you.
Okay, thank you for Ingrid's presentation on the microfluidic application, and I'm going to present another BioMEMS sensing application, which is tumor and cancer detection. As we all know that tumor and cancer is one of killing disease we are facing currently, and although there's numerous methods they will be presented, but they all have some kind of drawback. For example, like overdiagnosis, or like for breast cancer, they have some radiation exposure. So there is much more space for the development of the sensing mechanics. So today I'm going to introduce two mechanics in brief, and I will welcome any question after my presentation. So the first one is a probing, which proposed by the University of Maryland, and this is the structure they have. Is quite flexible and small compared to a dollar, I think, United cents or something like that. Yeah, and their aim is to detect the difference between the benign tissue and the cancerous tissue in the breast tissue core. And this is the fabrication of the structure, which is quite standard. And one noting point is that all the material they use is biocompatible. And the mechanism, because they want to detect both mechanical and the electrical signal from the cells. So for the mechanical part, the sensing principle is quite simple. I think all have learned from the lecture, which is the piezoresistivity. So when this pillar is pressed on the tissue, then it will cause some displacement in the substrate, and this generates resistance and electricity signal. So from that signal, we can see how the stiffness and the elasticity of the tissue. And the other is electrical sensing principle, which is adapting a conduction path from the top electrode, which is a pillar. Although the pillar is actually SU8, but it's coated with gold, so it is conductive. And this one is a tissue, and the bottom one is a supporter for the tissue, is also conductive. So there will be a conduction path from here. So by this conduction, you can actually see what's the conductivity of the cell. And besides, it's a quite clever design because it's also acts as an indicator. So when you receive some kind of electrical signal, you know that your probe is actually contacting your cell rather than your probe is like in the air or something, getting some random signal. And this is their calibration method, which I'm not going to details, but one is they're using a known cylinder with a known radius to calibrate the surface strain, and the equation is provided. And also one is they using a AFM tool with a known forcing applied to the pillar and to calibrate for the spring constant of the device. Okay, this is the setup. Quite, it's very I think it's very understandable. So this 3D printed a core, and the rod part, the device which is here, very small, on the tissue, on the core, and then they press down to the tissue to measure the characteristic. Okay, so here is the result, and you can see that at the higher displacement when it is contacting, the cancerous tissue and the benign tissue have actually different response to it. So the cancerous tissue is more stiffer, and the elasticity, which is calculated by another paper, not this paper, the adapt method from the other paper. But you can see that the benign tissue has a larger elasticity than the cancerous tissue. And for the electrical response, that is more clearer. It's clearer. So the conductivity of the cancerous tissue and benign tissue is quite separated. So by detecting both electrical and mechanical property of the tissue, they can actually have more accurate detection of the cancerous cells. But however, there's major problems that, from my perspective, is the advantage is more accurate, but the disadvantage is that they cannot detect early stage cancer because the cancerous cell concentration is very low. And the other very severe problem, which I somehow regretted choosing this paper, is that they state that they only use one sample in cancerous tissue and the one benign tissue. So it's not very persuasive, the result. They may contain some of errors. And the other method that is more convincing is the filtering method proposed by, I think, multiple universities. And this method is more on physical side, so it does a filtering, and they have two designs. The first one proposed at 2007 is the membranes is aligned. So the second design is just a misalignment in the membranes, because the misalignment allows you to have less force exerted on the cells, which can have less damage to the cells. And this is the design one. Design one. Okay, I just state that the design one is different. Is just the alignment of the two different membranes. Okay, this is the fabrication process. Also very standard and easy to understand if you have some basic knowledge of the fabrication. Okay, for the testing, okay, which this is very lengthy, so let's go back to the first page and see how it's going to test. So now, so they actually take some blood from the whole blood, and they eject some cancerous tissue, which is for specific, is circulating tumor cells, and then they're going to press this on the membranes. We're using some constant pressure, and after that, because the CTC is larger in size than other blood tissue, so it will stay there, it will be trapped. So later they apply some electricity to the cells, and the electricity do some chemical process and then detect for the CTC sequence. Okay, here is this is the first device result. This is the second device. Of course, I can see from the efficiency that the first device is more effective in terms of getting more CTC cells. But the second one can preserve more complete cells, which is actually the interest of their research. And both of the processing takes only few minutes, so they can complete. So it's quite fast compared to those taking hours. Yeah. Okay, so the advantage of this method is they have higher efficiency, and they can actually attract those cells in very low concentrations. But the drawbacks is that there might be some cells compatible to the size of the CTC, which will disturb the final results. So this is the I have presented the two methods of detecting the cancerous cells, and now I will handle my time to Kosti to present the application in scanning marrow in biosensing.
Thank you, CG, for the presentation. Very nice. And now I will move on to the next part of my my presentation. This one is the title. Okay, in my presentation, I will highlight and more focus on the working mechanism of the device. So this is my outline. I will talk about the MEMS micromirror and integrate it with the 3D SSOCT, and I will present the result and the conclusion. Okay, so first, the introduction is we'd like to tell you about the we'll tell you about the functionality of the device. The device is to do the imaging in vitro and in vivo. In vitro means that you take the sample from the structure, you cut it, and then you measure in the different place. That's in vitro. But in vivo is you image the structure directly to the structure. So you, for example, in this paper we talk about the image the human finger skin. So the imaging directly attached to the human finger skin to do the imaging. So that's for the in vitro. We use biological samples, which is onion peel and pickle slices. For the in vivo imaging, we use a human finger skin. So what's the advantage of this device is that the things, this one, skin surface, finger, sweat gland, and the other, etc., is clearly visible and clearly distinguish each other. Oh, now the device that we use is SSOCT. So we have to be familiar with the SSOCT. SS means swab source. So it means that the wavelength can be varied over time. OCT, the O is optical, so we use a light, we shine the light. Coherence means that the interference of light with constant phase difference. What means that optical coherence means that when we have two light with the phase difference, from that phase difference we can know how is the sample looks like. And tomography is we do imaging by section, so we use slices, and then if we combine each other, then we have a 3D image. That's tomography. So next, okay, this is the MEMS micromirror. Quite interesting because we have learned a lot of the class about this one. So I think it's quite easy to understand, not difficult. So I will highlight the working mechanism. So this one. This one is we use a vertical comb drive actuator. So if we give a bias, if we give a bias here and here, so it will make the device will be, and this side will be bending downward and this one will be bending upward. So if we give AC bias on these two actuator, we give AC here and AC bias here and here, it will rotate in this way. Then for the mirror in the inner part, you will see that this is the vertical comb drive. If you give bias here, so it will rotate in this way, right? This way. Bias here, bending downward here. If bias here, bend downward here, so it will rotate in this way. It's quite easy, right? So if you are still not understand, I will give a video. Then you are more, like definitely you can understand the working mechanism. Okay. Oh, there's a sound. Where's the sound?
F2.
F2. Yeah. Okay. Oh, but not too loud because it will be noisy. Okay.
We have designed tiny actuating systems that pull the mirror and make it rotate about the two axes.
You see, right?
These systems are known as vertical comb drives.
Yeah, this one.
A vertical comb drive consists of two sets of combs made of conducting silicon. One comb, called the rotor comb, is attached to the mirror and placed higher than the other comb, called the stator comb. When a voltage is applied to the stator comb, a positive charge.
Okay, so yeah, it's easy, right? So it's clear enough, I think. So we use the actuator, electrostatic actuator, vertical comb drive. You see the inner resonance is higher, right? The order is kilohertz, while the outer is just 100 hertz, the 300 hertz. Okay, next. Okay, now we integrate the mirror to the SSOCT. So, like I said, that the SSOCT, this is the swept source. This is the source of the light. Go here, go to the interferometer, and then yeah, this is the reference arm, and this is the sample arm. So basically, in this part, we have a sample, right? So the phase difference between here and the reference will be different. So after that, the reflection of the light with the phase difference detected by the photo detector here, and then based on the phase difference, we can understand how is the sample look like. Okay, this is basically the working mechanism. Yeah, this one is the explanation. You can see, you can read yourself. This one, similar to what I explained earlier. So this is the properties. You can read by yourself, and this is the result. So you see, in this part A, this is the pickle slices. In this B also pickle slices, but not using the SSOCT MEMS mirror. This is using the MEMS mirror. So by having this MEMS mirror, by using the 3D SSOCT, we can more clear image here rather than this one. We can clearly visible distinguish each part of each part. Then, this one is not clear enough because this is not using the SSOCT MEMS micromirror. And this one, the onion peel, different. This is the A and B is the pickle slices. The C is onion peel. Okay, and this one for the EE4 imaging. So this one is the image, right? We can see clearly distinguish the epidermis, skin surface, fingers, slit glands, and the other, etc. And this is the tomography slices. What I mean is the slices. If we combine it, we can see a 3D image here. Okay, so I think this is the end of my part. Now let's Junho explain the next part. Okay.
Thank you, Eric. Okay, here comes my part. The topic is implantable X-ray-based blood pressure microsensor. So I think this is a very interesting and very unique design, and unlike many other systems, it's very simple in structure but very useful in practice. So I think that is also the beauty of our engineering. Okay, before we talk about the sensor itself, let's look at the background that it's designed to solve. We know that the disease, coronary artery disease, is a leading fatal disease in our modern society. It's caused many of the deaths. And the common treatment is a PCI with a stent. That means we use by injecting a stent into your blood vessel and to your heart, and enlarge the stent so that the blood vessel will be enlarged, so that the blood supply will be sufficient for the heart. So that in this case we can solve the problem called AKA heart attack. But there is a common drawback for this treatment is that we call it restenosis. That means the stent cannot hold its original position, especially for a long time. So there's a chance that the stent will go back to its narrow position again, so that the problem come back again. So clearly there's no really good solution to solving with the restenosis. So a periodic monitoring is essential. And thanks to the modern technologies, many methods are options, but I can say that none of them are really suitable for this purpose, because they are either too expensive that means over $10,000 for one-time check, or even invested to our human body. Every time you want to do a test, you need to cut your blood vessel. And some of them are just low resolution and not suitable for the work, because our coronary artery, the blood vessel, is very small in size. And some of them are even worse, it's too radioactive, it's not allowed to be used for the screening purpose. And currently there are also some existing blood systems that are designed for some similar purpose, but they are just too large in size because we are dealing with the 2 to 4 millimeter of the blood vessel size. Okay, so here comes the solution. In short name is XBP. So this solution, I think, is very interesting and unique. It's like that. It provides a solution from 0 to 1 because it really can help the people to prevent from the restenosis. So really to help people save people's life. Okay, it's very simple in structure. As we can see here, it only has 3 major components. One is the pressure exposed membranes. Here. it can be deformed under the blood pressure. And another one is a micro reservoir filled with X-ray visible fluid. It's organic fluid that's used for the X-ray. And the next one is a microfluidic gauge. As you can see here, it's filled with air. So all this material are just simply made by the silicon oxide, silicon nitride, or some glasses. So it's biocompatible, so basically injected into our body and it will not cause any side effects. Okay. So how does it work? Just we can see from the picture here. As you can see, when we put the sensor at the very initial position, at the initial position, we fill the micro reservoir with liquid and fill with microfluidic with air. So we put the sensor into our blood vessel, and under the blood pressure, the membranes will be deformed and press the liquid into the gauge. So with the help of the X-ray, in the X-ray image, we are able to find the length of the liquid in the gauge will be different and different pressure. So we can get the reading of the pressure through the length of the gauge. So how do we detect the restenosis? It's also very simple. We put two sensors in front and the back of the stent. So if the restenosis happens, so that means it get back narrow again. Of course, the incoming blood pressure and output blood pressure will be different. So simply by measuring the pressure difference of the incoming and output, we are able to detect whether there is a restenosis or not. Simple like that. Okay, the fabrication process, and again, due to the simple structure of the sensor, the fabrication process is also not that difficult to understand. We're just using some existing methods like the DRIE and the LPCVD, like we're using the DRIE to etch the curve here, and using the thermal oxide and the LPCVD to get the silicon oxide and silicon nitride forms, where the silicon nitride form is used as the membranes here. And then we just attach the Prix wafer, which means the glass wafer, the transparent glass, on top of that. And then we etch another again from the back side so that we can expose the membranes. And then fill by the filling of the liquid. Of course, before the filling of the liquid, we need to we add another hydrophobic solutions to create a coating for lubricant purpose. That's all. Okay, of course, before we put the sensor into real practice, of course, we need to build up the relationship model between the pressure and the length. So the deductive function is here, and based on the deduction function, we are able to plot the relationship lines between the blood pressure and the length in the gauge.